Alright, this is 6-1, the first lesson in the unit about circles, Unit 6. The first 2 pages of these notes have a bunch of definitions and examples over here. They're pretty self-explanatory, so I will let you copy those down and interpret them because I think that you can. They should be in the notes copied in Canvas below. The one thing that I will add from these 2 pages is that some notation things. And this is because we're going to spend the next couple of months in geometry, and for geometry it's really important that we are communicating accurately about different things, right? So if I'm talking about a point, I want you to know that I'm talking about a point, which we do with notation. So I will just give you these really quick. A point has like a miniature point in front of it, and then you write the letter of whatever point you're talking about. For a line segment, which is a part of a line, meaning a line in geometry goes on forever in both directions. A line segment is just a piece of that line, so you use the endpoints of that line segment as your 2 points, and then you put a little line over it. For a full line that goes on forever in both directions, you can use any 2 points on the line, and then you need arrows on the little notation above it. For angles, you need 3 points, so they make sort of that V shape, and then you would put a little angle symbol in front of it. MathSpace actually has that angle symbol for you to type in sometimes. So a little angle, and then we have A, B, C, because B is, we sort of go in order here. Let me use my pointer. We go A, B, C. The order of the points is not important, except that the middle point has to be the vertex. The middle letter in your list has to be the vertex. Otherwise, it won't make sense. The vertex is just the bottom of the V shape of an angle. Then we have arcs, which you'll have the definitions for above. A major arc is more than half of a circle. The problem with arcs is that if we use just 2 points, because the circle is round, it's unclear which direction we're talking about. So if I just say arc FB, are we talking about this arc, or are we talking about this arc, right? Because they're round, so it goes both directions. So to indicate which direction we're going, if we're going the long way around the circle, we use 3 points instead of 2. So I would instead say arc FCB. That indicates that I'm going the long way around the circle. For minor arcs, which are less than half of a circle, you just can use the 2 points, and we assume that we're going the short way, because that's the notation for a minor arc. For semicircles, which are exactly half of a circle, say like DE is a semicircle, that one, it doesn't matter if you use 3 or 2 points, because it's much the same either way, and so the notation varies depending on who's doing it. So that's some notes on notation. I will let you find examples of the definitions in this picture. For some of them, I will say that there are multiple examples. For example, like radius, there are several radiuses that would work as radiuses. So I only need one example, and that's definitely enough of an answer. Oh, look at that. I forgot to erase the page. Let me do that. There we go. And while I'm at it, okay, that's what happens when I'm late on these lessons. So the next thing we're talking about here is arc measure. And so we talked about arcs for a second there, but arcs are just a part of a circle. And arc measure is a way that we measure arcs, I guess. But it's very important that you know that it's not the length. So when we say arc measure, we're not talking about how long the curve is. We're talking about how much of the circle it is. And it's defined as, yikes, it's too much, as the same it's like a degree measure that we use for arc measure, and it's the same as the central angle that could be attached to it, right? So here's our arc between these 2 points. If we make a central angle, which you'll have learned the definition of in the previous 2 pages, a central angle occurs, like, has the vertex in the middle of the circle. Think a clock when you think central angle. So a central angle is the same degree measure as the outside. So this, I think, is like 100 degrees about in this picture, and out here the arc measure is also 100 degrees. So those 2 things are the same because we've defined them using each other, right? So the arc measure is the same as the central angle that that's attached to it. So these 2 things are equivalent. Just a little notation for you, because there's lots in geometry. The little m is just measure. So what this is saying is it's the measure of arc BC is equal to the measure of angle, let's put a little angle symbol, CAB. So those little n's are just talking about the measure of, because we will have different things like arc length instead of arc measure, so we need to know that it's measure. And we are just using degrees when we measure angles. Something that will be useful for you to remember is the measure of a whole circle. A full circle is 360 degrees. Whole circle is 360 degrees. A half of a circle is 180 degrees. Both of those are useful for us. Yeah, we'll see why in a second. So for this first example, we have the measure of this central angle here, and it's asking us for this arc measure. That's what it's saying, the measure of arc BC, which we just learned that those 2 things are the same, right? If the central angle is 90 degrees, the arc measure is also 90 degrees. So that one's super easy. Those 2 things are equivalent because they're defined with each other. For number 2, it's again wanting us to find this arc BC, but instead of giving us this angle, which is the one that we need, they gave us this one. So this time we will need to use the fact that a whole circle is 360 degrees, so that we can take away from that 261 and find this leftover angle in here. So that math looks like 360 minus 261 equals 99 degrees. So this is 99, and so is this. So that is the measure of that angle and the arc. One more here, we have a diameter of our circle, so this is a half of a circle right there, and we have 70 degrees over here, and what we're looking for is, I should have highlighted those the same color, here you go. What we're looking for is that green central angle. So if we know that the full yellow angle is 180 degrees, we can use the same logic that we've been using to take away 70 from 180 to find what's left for this angle, which is 110 degrees. So if this is 110, so is this. So central angles and their attached arc measures are the same. That's the moral of the story. This activity down here, that we're not going to do this, partly because you're at home and partly because we tried it in class and it took too long. So instead, I will just tell you things, which is not always good, but in this case, we're going to say it's good. We have now inscribed angles thrown into the mix here. So we still have the two, the central angle here and the arc measure out here. But then we have this inscribed angle, which you would have learned in your definitions, is a kind of angle where the vertex is on the other end of the circle, or really any edge of the circle. And it turns out that when you have both of these kinds of angles, an inscribed and a central angle attached to the same arc, then they all have sort of a special relationship. This angle, these two are equal. We just learned that. Those two are the same. These two, though, are, the central angle is twice as big as the inscribed angle. Usually I can point, sorry. So if we multiply the green angle by 2, then we will get the blue angle. And also the arc on the outside, right? Because the blues are equal in this case. So this formula over here is just missing times 2 right here. Because what we do is we multiply the green angle by 2 to get the measure of arc BC. That's what this says. But also the measure of angle BAC. Because there's the central angle would be named BAC. So a lot of your homework for this unit is either multiplying by 2 or dividing by 2, because you're either finding the central angle from the inscribed angle or you're finding the inscribed angle from the central angle. So you either have to multiply by 2 or divide by 2, depending on which direction you're going. So remember, I want you to notice that visually, this angle is much bigger than this angle, right? In fact, you could fit exactly 2 of those angles inside of the central angle. And so you have the power of vision on your side, right? Because you can tell visually which one is bigger. So on your math space, when you're given something like, I don't know, like a inscribed angle with a central angle like this, you can visually tell which one is bigger. And so you can tell which direction you're supposed to be going. Like this would not be a divide by 2 situation because this one is bigger. So you can visually tell whether or not you should multiply or divide by 2. On this first one we have the arc measure. So not a central angle but an arc measure, which really are the same thing. And then an inscribed angle because it's touching the other side. So because this is 120, this should be half as big, right? This time we're dividing by 2 because we're going into the circle, which gives us the measure of 60 degrees for that angle. On number 2, we have 2 inscribed angles attached to the same arc on the outside of the circle. So just follow me really quickly. This inscribed angle here is 33 degrees. So if we were going from 33 degrees inscribed, that would give us a 66 degrees arc measure, right? But now we have this angle, this inscribed angle, attached to the same arc. So that means if we have 66 degrees out there, we should divide by 2 to get angle A, which is also 33. So that's our little logic there, but anytime you have 2 inscribed angles attached to the same arc, they're going to be equal because they both have that half relationship with the arc measure, so you might as well assume that both of them are the same. You can't divide by 2 in any different ways, right? There's only one way to do that. Actually, I'll talk about math space in a second, but last one, we have a triangle inside of a circle, and you might be thinking, okay, where are the angles inside this? And I will tell you that their triangle has 3 angles. So we're going to ignore that other line here, and we're going to focus on the fact that we have an inscribed angle attached to an arc of 180 degrees. This is our inscribed angle. So if this is 180, we should be dividing by 2 to get the angle B, which is 90 degrees. Divide by 2 there, right? So that would give us 90 degrees for angle B. And then we have another one of those same relationships here. We have an inscribed angle attached to an arc. Yikes, that was not a good arc. Of 30 degrees. So same thing, we should be dividing by 2 to get inside of to get the inscribed angle in there, which if you divide 30 by 2, you get 15 degrees. And then the last one is kind of a mystery, right? So we have angle A that we're looking for. This arc measure is not given to us. And so we have a couple of different options here. We can either find out what this arc measure is using the fact that a full circle is 360 degrees, and we just take away 180 and we take away 30. Or we could use a different geometry fact that we haven't talked about yet today, that triangles have an interior angle sum of 180 degrees. So we could also take away the two angles we found from 180 to find the missing angle. So we sort of have two avenues. I'm going to do the one about the arc measures because that's the one we've been learning about today. This is 180 degrees, and I've already used 30 of those 180 degrees, which means this should be 150. And then dividing that by 2, gives us angle A, and that is 75 degrees. You would get the same degree measure if you subtracted the two angles we already had from 180, because conveniently math does that. We love that about math. Here's this. So those angles are related to those arcs in that way. I will say on MathSpace there is a question that I want you to skip if you haven't done it already, and I will write it here. So skip number 15. That one is about its proofs, which are really important to learn how to do, but proofs on MathSpace are kind of nonsense because they want a very specific thing, and that's not how proofs work, so we don't like that. Anyway, so skip number 15, I keep forgetting to take it off. There are some questions that give you, or ask for a reason for your answer, and then they give you like a giant list of reasons to look through, and truly there's like hundreds of options. So I will tell you that most of your reasons will be one specific reason, and you can find that reason by typing in, like typing in twice, the word twice. It brings up the reason that central, or it's something like angles at the center are twice the angle at the edge, or something like that, right? So that's the one that you use most often. There's like mostly it's that one. So you can search the word twice and only that option comes up. There's another one where it looks kind of like this problem with two inscribed angles. That one you can search the word inscribed. They actually use vocabulary words on that one, which is convenient. That one you can search inscribed, and it comes up with a reason, something like two inscribed angles on the same arc are equal. That's another reason that you'll need to use, but this one only occurs once. You'll only need to use this one once. Lots of math-based things today. I'm going to keep going here. Do I have room? Kind of. I will move stuff over so I have room. There's also a question number 12, which the question is really good, but the way that they want you to answer it is very confusing. For example, like pretty much everyone who tried this problem got it correct, but the MathSpace wants you to show a bunch of nonsense work before you give your answer. So what I'm saying is you have the skills to answer this question. MathSpace wants you to answer it in a very specific way, which is kind of frustrating. So on number 12, it will give you something that looks like a circle with a triangle inside of it. It'll give you one of the angles, and then it'll ask for x for that other angle. So the student that I helped with most recently had the number 59 in that angle. And then these are labeled A, B, C. So the the first thing it wants you to type in, and I know that this is kind of nonsense, so that's why I'm giving it to you. The first thing it wants you to type in is 59 plus the x angle plus, and it wants you to type in the angle symbol ABC equals 180 degrees. So what we're starting with, I guess, is the fact that all of the angles inside of the triangle add to be 180. Don't ask me why. There's really so much of an easier way to solve this problem, and most of you will default to that way and then be like, why do you want something different? So I'm giving you this. So when you type that in, it will then give you, and then it'll ask for a reason. If you type in 180 degrees, searching 180 degrees in the reasons, a reason will come up that just says the interior, there's a couple with 180, so you have to actually look for this one. Interior angles of a triangle, interior angle sum of a triangle is 180 degrees. So there's a reason that says that, and it'll want you to put that in. Then it'll go back and say, okay, what's next? So then you say angle ABC equals 90 degrees. And then it'll ask for a reason, and you can search semicircle, and only one reason will come up. Pick that reason. And then next it will let you put in the equation 59 plus x plus 90 equals 180. So those are just all of the angles inside of the triangle adding to 180 degrees. After you put that in, it will let you put in your answer. It will let you put in x equals whatever you get. So hopefully that helps. Hopefully you haven't all done this problem already. It's annoying and I need to change it. I will do that eventually. So that is all my math-based junk for you. Number 12 is nonsense. If you follow this, though, you can get the math-based to cooperate with you. These are some reasons that you'll need to search for, and skip number 15. Cool. That's all.